This is part 6 in our series of lectures on other forms of induction. In this lecture, we're going to write a proof using the principle of complete induction of the existence part of the Fundamental Theorem of Arithmetic. Remember that the Fundamental Theorem of Arithmetic tells us that every natural number other than 1 is either a prime or it can be written as a product of primes. And moreover, except for the order in which the primes appear, that factorization as a product of primes is unique. So we're not going to worry about the uniqueness part in this lecture. That's a little bit harder, and we'll return to that in a future video. We're just going to deal with the existence part. So here's the statement of the exercise. Prove that every natural number is either 1, prime, or it can be written as a product of primes. And we're going to do it using the principle of complete induction. The idea of the proof is that if we gave ourselves a natural number, say it's bigger than 2, bigger than or equal to 2, if it's not prime, then it must have a divisor other than itself, and therefore it can be written as a product of two smaller natural numbers. So if we're using principle of complete induction, since those numbers are smaller, they're predecessors of the given number, then we have the right to say that each of them, by the inductive hypothesis, can be written as a product of primes, and that in turn would give us the original number written as a product of primes. So that's the idea of the proof. It's really not very difficult, and it's perfectly set up for the principle of complete induction, because the inductive step involves smaller numbers, but not the immediate predecessor. So principle of mathematical induction wouldn't be strong enough to prove the result. So see if you can give the proof a try. It's really not that difficult. Well, at least write down what is the beginning of the proof. Put your video on pause and give it a try. So here's the beginning. We define S to be the set of all natural numbers which are either 1 or prime or a product of primes, and we have to prove that S is equal to the set of all natural numbers. Now see if you can do the basis step. It's really very simple. Here's the basis step. We just simply have to verify that 1 is an element of S, and that's completely obvious because there it is. Now see if you can prove the inductive step. That's a little bit harder, but I told you the idea a minute ago, so see if you can write it down as a formal proof. Put your video on pause and give it a try. So here's my proof of the inductive step. I let n be a natural number, and I suppose that n is at least 2, and all of its predecessors in the set of natural numbers lie in S. Why did I say 2? Because 2 is the first natural number which I haven't as yet verified lies in S. Right? So far we've only verified that 1 is in S. Now if n happens to be prime, then by definition it's in S. If it's not prime, then we know that it has to have a divisor, and therefore there must exist natural numbers a and b such that n is a product of those two natural numbers, and neither of them can be 1. So it follows that both of them must be less than n, and therefore they both lie in S because they're predecessors of n, and therefore they are each either prime or a product of primes. We're thus able to deduce that the product is a product of primes, right? Because A is a product of primes, B is a product of primes, so that when you multiply it together, you get another product of primes. So that shows that n lies in S. And so we have the right to say that by the principle of complete induction, S is equal to the set of natural numbers.